In the last segment, we derived these lovely equations, the zero order, the first order, and the second order integrated rate laws. Remember, these are called the integrated rate laws. And we use them to say, hey, let's test some data and see whether it's most consistent with a zero order, first order, or second order rate law, and that helps us determine a rate law for a reaction. Is there anything else we can do? Well, I mean, the one thing these are often used for is if we know a reaction is zero order or first order or second order, we can use it to determine the concentration of one of our reactants at any given point in time. So if we use the example we had from the slides in the last video, we had the N2O5 reaction. We saw that K was 0.0069 per second for N2O5. And our rate law was first order. So we saw that rate was equal to K times the concentration of N2O5, which means that our integrated rate law for this one is going to be the natural log of the concentration of N2O5 at any given time is equal to minus KT plus the natural log of N2O5 to begin with. And so we can use that to find out, if we know the initial concentration, the concentration at any given time. We can also go backwards in time. If we know the concentration now, we could find the initial concentration. If we know two concentrations, we can find K. So there's all sorts of things we can do with this relationship. But let's go ahead and do one. So let's say we know that our N2O5 initial concentration was 0.050 molar. And we want to know, what do we have 10 seconds later? That's a perfect example of one where you'd use the integrated rate law. I know some concentration now. I want to know what it is later. That is integrated rate law right there. So if we know K, turns out there's other things we can do. So I wouldn't use that as a 100%, but that's certainly one of your first guesses. Hey, can I use the integrated rate law in this case? So what are we going to do? We're going to say the natural log of N2O5 at any given concentration or any given time is minus KT, et cetera, et cetera. So we get the natural log of N2O5 at any given time is equal to minus K, minus 0.0069 per second, times T, in this case is 10 seconds. Let's put a dot there so we have a couple sig figs. And then plus our initial concentration. And so it's going to be the natural log of 0.050. And so in this case, it's just pretty plug and chug. You're going to plug that into your calculator. One important thing to keep in mind is that these units got to match. Right? Occasionally, you're going to say, oh, I want to know how many hours later is my concentration. And if your K is in units of per second, you got to make sure to do that conversion. Our concentrations have to be in molarity because that's kind of how we defined all these things. And so that's just what we get. So if you do that, you get the natural log of N2O5 at any given time, or at this time, I should say. So I can even put a 10 there if I really wanted to. Most people won't do that. Most people will still write the T. And that is going to be negative 3.06. How do I solve that? Well, I just take the exponent of both sides. So I take E, and I get the concentration of N2O5 is E to the minus 3.06. And if you plug that into your calculator, you should get 0.047. Don't forget that molar at the end. It's really hard because, right, we didn't have concentration units when we took our natural logs. We just didn't even put them there because you can't take the log of a natural unit, the natural log of a unit. And so how do we get that unit back at the end? Remember, there's that kind of tricky thing I said, oh, we divide by reference thing. You do get those molarities back at the end, so you got to make sure when you're recording your final concentration that you put that molarity back on there. And so I got 0.047 molar. All right, here's something for you to do. I've got a rate law for a reaction. It's K times NO2 times F2, and I want to know which of the following plots is going to be linear. So I'm going to pause and make a funny face, because what I found, the reason I make the funny face is, just so you know, is what I found is when I don't make the funny face, the frame that it pauses on always have a funny face. So I'm like, might as well make them on purpose. So here you go. Okay, what did you come up with? Well, you're like, hey, the reaction is first order in NO2, and it's first order in F2, but it's kind of second order overall. So I know a lot of times people will run over to this one, and they'll say, well, since it's second order overall, I should be able to plot 1 over both of those. And it doesn't work that way. It doesn't work where you can take 2 different reactants, multiply them by each other. If it was second order in NO2, 1 over NO2, yeah. If it was second order in F2, 1 over F2, absolutely. But not 1 over NO2 times F2. So it's not that one. The other thing is, right, we have to know, is first order in NO2. Why? Because there's a 1 there implicitly. And so we just have to know that our natural log of concentration versus time is the one that we're going to see as first order. F2, NO2 versus time, 1 over F2 versus time, those are 0 order and second order tests, and so they wouldn't necessarily be linear. Okay. So very easy, once you understand those different degree rate laws, to identify which one to use if you're trying to work with a particular equation. All right, so let's keep talking about the same reaction and talk about something called half-life. So we've got N2O5 making NO2 and O2. We found the rate law. We used the integrated rate law in order to find out at any given time. We had our K value of 0.0069 per second. What I want to know now is how long to go from 1.0 molar down to 0.5 molar. So, right, half-life. Let's figure that out. Natural log, my final concentration. People get this confused a lot. My final concentration is 0.50 molar. I'm going to put that 0 in there. I want those couple sig figs. 0.50 molar. Now, I put the m in there. Technically, I shouldn't. I should just say 0.050. Is minus 0.0069 per second times t plus the natural log of my initial concentration, which is 1.0. Okay. People get those 0.5s and those 1.0s mixed up quite a lot. If you do, you end up with negative values other places. So if you're like, why did I get this negative here? Let me just pretend it's positive. No, you probably just switched a couple things in there. Very easy to do. So natural log of 0.5, natural log of 1. That is just some work. Natural log of 1 is 0. And so you can solve this. I'm not going to show you all the work for it. It's mostly just calculator work. And I get that t is about 100 seconds. Okay, so I get about 100 seconds. I'm not going to worry too much about the details. So that's how long it took to go from 1 molar to 0.5 molar. Some people, they're like, well, if I went from 0.5 molar to 0 molar, that should also take 100 seconds, because it took 100 seconds for the first 0.5 molar, and it took 100 seconds for the second 0.5 molar. But it turns out that's not quite true. Let's figure this out. How long from 0.5 molar to 0.25 molar? We set up the equation just the same. 0.25 equals minus 0.0069 per second times t plus the natural log of 0.5. Plug that in, and guess what you get? You get t is about 100 seconds. So it took us 100 seconds to go from 1 molar to half a molar, and 100 seconds to go from half molar to 0.25. That's less. I mean, we used 0.5 molar in the first half. We used 0.25 molar in the second half. Why did it take the same amount of time? And this is a natural result of a first order reaction. It is the half-life, whoa, that's an interesting H, the half-life of a first order reaction is constant. It doesn't change. And so if I wanted to know how long it was going to take to go from 0.25 to 0.125, it would be 100 seconds. 0.125 to 0.0625, so 0.6125, yeah. Then it would be 100 seconds. Right? So that's what it means by it's constant. When you half, it's always going to be the same time. Why is that? Why isn't that if we use 0.5 in the first 100 seconds, we're going to use 0.5 in the second 100 seconds? Well, if you think about the chocolate pouring, right? As you have less and less of it, your rate is decreasing, right? The rate of this reaction is decreasing over time because it's dependent on how much we have. So the less we have, the slower this reaction goes. And it turns out just mathematically, it works out perfectly that it always takes the exact same amount of time to get half. And so we call that the half-life, and you can calculate that, right? So if we want to generalize that, we could say the natural log of concentration of A naught over 2, right? We want to figure out how long does it take to get to half of our initial concentration is minus KT plus the natural log of the concentration of A naught. Right? I'm not going to do all the algebra work here. You can find it in your book. You can find it online. What you end up with is that if you solve this, you get that T is related to the natural log of 2. Most people will just use the numeric version, 0.693 over K. So a constant. K is a constant, 0.693 is a constant, and so you get that. And people usually call this the half-life. So they say T1 half is 0.693 over K, and that's for a first order reaction, right? Not for any other reaction. First order reaction. Good equation to know, 0.693 over K. Well, we said it's true for the first order. How about for second order or zero order? So let's go ahead and do those. For a second order reaction, I'm not going to do all of the math for you. I'm going to tell you that for a second order reaction, that T1 half is 1 over K times our initial concentration. Okay? And then let's go ahead, this is for second order. Let's go ahead and give it to you for zero order. T1 half is A naught over 2K, and this is for zero order. And this is very interesting because you notice that the half-life in second order goes down as our initial concentration increases. Whereas in zero order, the half-life goes up as our initial concentration increases. And that seems a little weird. But remember, a zero order reaction is always going at exactly the same rate, 100 pounds of chocolate per hour. So if I have 200 pounds of chocolate, right, it's going to take me 1 hour to get half of that. But if I have 1,000,000 pounds of chocolate and I'm still going at 100 pounds of chocolate an hour, I've got to get down to 500,000 pounds. So I got to use 500,000 pounds of chocolate. That's going to take a long, long time. So my half-life goes up as I have more stuff. Second order, on the other hand, means that you've got that rate law with that square in it. The more you have, if I double my concentration, my rate goes up by a factor of 4. If I triple my concentration, my rate goes up by a factor of 9. If I quadruple, it goes up by a factor of 16. The more I have, the faster that reaction goes. And so that's what this A naught does in the denominator. It says the more that you have, the less time it takes to get half of that, which is a little counterintuitive. But it just means that this reaction is super dependent on the amount of A naught. If you have a lot of it, that reaction goes really, really fast like gangbusters, and so it doesn't take long for half of it to get used up. So knowing those three half-lives are really good. It's a good thing to be able to work. I'll always give you those equations. You just need to recognize them, and that's how you can use them. So let's go ahead and use it. We've got a reaction A, B, and C going to D, E, and F, and we want to know the half-life of the reaction that's second order in C. We've got a K value, and we're going to start with a concentration of 0.5 molar. So as soon as we know that it's second order in C, and that we're talking about half-life, we can just write down the second order half-life equation. T1 half is equal to 1 over K times the concentration of A naught. In this case, our A is C, so I'm going to go ahead and cross that guy off and put a C there. So 1 over K times the concentration of C naught. Pretty simple since we already have a K. 1 over 1.53 times 10 to the minus 7th per molar second. And then we're going to multiply by our initial concentration of 0.500 molar. That's just a math problem, right? Our molars cancel. We will end up with seconds because 1 over seconds gives me seconds. And so what do I get? I get 1.3 times 10 to the 7th seconds. 1.3 times 10 to the 7th seconds, which is a long time, just so you know. It's about 152 days. Okay, so this reaction would take quite a long time to go from 0.5 molar down to 0.25 molar. The question then is, how long does it take the concentration of 0.125 molar? And there's two different ways you could answer this question. So question 2 is the one we're doing right now. We did question 1, we're doing question 2. How long does it take to go if there's a concentration to a 0.125? When you see questions like that, usually one of the first things you're going to think of is the integrated rate law. Why? Because you have a concentration now, you have a K, and you want to know a concentration at a different point in time. That would be the integrated rate law. So we'd say 1 over the concentration of C at our time is KT plus 1 over the concentration of C at our initial concentration. So we could definitely use that and figure it out. We could also notice that our first half-life was going from 0.5 molar down to 0.25 molar, and this would be our second half-life, going from 0.25 molar down to 0.125 molar. And so that would be another way, is also notice that this is a second half-life. And if this was a first order reaction, we could just double that. We could say, oh, 152 days, let me double that in 304 days, boom, done. And it's tempting to do that. But remember, this half-life of a second order reaction is dependent on your concentration. And so here we've got T1/2 for the second half-life is 1 over K times my initial concentration, which was 0.250 molar. Oh, so that's going to change it, right? We've got a K value that you can plug in from above, and you get here that T1/2 should be double that. So we're going to get 2.6 times 10 to the 7th seconds, or 304 days. That's for the second half-life. That's not total. That's just to go from 0.25 down to 0.125. If I wanted to add it all up, I'd do 1.3 times 10 to the 7th seconds, plus 2.6 times 10 to the 7th seconds, and I'd get my 3.9 times 10 to the 7th seconds, or 304 plus 152 days, which would be 456 days. All right, so 456 days to do 2 half-lives, not just 2 times 150. Most people, like I said, will just use this one. I use this other one just to show you that it's possible to do, but hey, I want a concentration at a given time. I've got it now. I've got a K. Very simple, very easy to plug that in to the integrated rate law for the second order reaction. All right. One more thing before we go. Well, actually, I think of 2 more things before we go. We've got a 20-gram ice cube. It's melting on a rack. It takes 84 seconds for 10 grams to melt. After that, it takes 42 seconds for 5 more grams to melt. Based on that data, what order reaction is the melting of ice? Alrighty, go. Okay, what do you come up with? Well, let's see. We've got 20 grams. Right? That first 10 grams melted in 84 seconds. The second melted in 42 seconds. And when I look at that, I say, hey, I've got 2 half-lives that are not the same. So I'm going to cross off first order because I know that my half-lives are not the same, whereas half-lives in first order would be 84 seconds for the first half, 42 seconds for the second half. So then I got to look at my 2 remaining ones that I know. I'm going to guess it's not third since we haven't talked about that, but let's figure it out first. 0 order, if you remember the half-life equation for 0 order, is the more we have, the longer it takes, right? Because if we have 1,000,000 pounds of chocolate, we're using it at a constant rate, then it takes a while to get to a half. Whereas the second order, the more we have, the less time it takes. So when we had a lot, it took 84 seconds. When we had less, it took 42 seconds. And so if I were to guess, and I were a betting man, I'd go ahead and bet on 0 order. When we had more, it took longer. When we had 1,000,000 pounds of chocolate at 100 pounds an hour, it took longer to get half than when we had 100 pounds of chocolate in 100 pounds an hour. So, is this true? Is melting a 0 order reaction? The answer is yes, it is. It doesn't matter how much ice you have. It matters how much heat you have. And heat is relatively constant. And so if you've got a bunch of heat, it's going to melt a certain amount of ice. And so it's a zero order reaction. It doesn't depend on how much ice you have. It depends on how much heat you have. And so yes, this would be a zero order reaction, and all phase changes are zero order reactions. The more you have, the longer it takes. So we're going to cross off that one. We didn't talk about the third order reaction. I'm never going to have you do a half-life of a third order reaction, so you don't have to worry about that one. So that's one thing. And it does have a different form. You could imagine that in a third order reaction, the more you have, the even faster it goes. And so you'd have a very, very short half-life for the first half and a longer half-life for the second half. All right. Next question. What order is OH minus in the rate law for the reaction of OH minus with CO2? So this is a review problem. I'll throw those in there every once in a while just to see if you're paying attention. So go ahead and try that one. Okay. What'd you come up with? Hopefully you looked at this and you're like, hey, this looks like probably an initial rate problem. Even though I didn't use the word initial rate here, I probably should have. Sorry if that confused you. Even though I didn't use it there, it's probably an initial rate law problem. So what we have to do is we're looking for OH minus. We have to look for a set of experiments where OH minus doesn't change. Or sorry, where OH minus changes and CO2 doesn't change. And that's experiment 1 and experiment 3. OH minus goes from 3.0 to 4.5. CO2 stays at 5. So when I go from 3.0 to 4.5 molar, that's a factor of 1.5 times. When I go from a rate of 10.0 to 22.5, if you get out your calculator, that's 2.25 times. Well, 1.5 is definitely not equal to 2.25. So it's probably not a first order. So how do we know what it is? Well, it's not zero order because the rate did change with our concentration. There we go. 1/2, second, or third. What do we have to do? We have to figure out, we did a rate, or I'm sorry, we did a concentration change. What power is going to get us that rate change? You could do the mathematical method if you wanted to, or you can just kind of figure this out and be like, well, if I raise it to 1.5 squared, what do I get? If I raise 1.5 to the 1/2, what do I get? And it turns out, if you do this, you get m is equal to 2. 1.5 squared is 2.25, and that would tell us that we had a second order reaction. So we can use that data, tables of data like that. If we have a bunch of different rates and concentrations, you're probably looking at an initial rate law. If you just have a bunch of concentration data without some rates, you're probably looking at the integrated rate law. And the end. I thought there might be another slide, but there's not. Hope this was helpful. We'll try again in a little while. Bye.